how it starts. We go back to your house.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. In this example, we have a pendulum, or maybe a person in a swing, if you will, that starts from a horizontal position. And it swings all the way down through an angle theta. We would like to know how much work does gravity do on the object throughout the trajectory all the way down. We can evaluate this by calculating the work as follows. So we start with the formal definition F dot ds. And we have to evaluate this integral at every single point on this path. So mg, so this is in fact the force F, if you will, like this. And at that point, or any given point on the trajectory, it goes through a small displacement in a certain direction. So here we have ds. And the angle that forms between the horizontal and the radius, theta, is also found here. You can imagine that all the way to the top it's 0 and all the way to the bottom it's 90 degrees. So they are identical. And how do we calculate the cross product or the dot product? So the dot product is, in general, it's the force times displacement times the angle between them. And here we see that the angle is, or the cosine of the angle. So the angle is theta, so we have just cosine theta, like this. Here we are integrating over S, the displacement along the path. But then we have function that depends on cosine, so we have to do something to fix the situation in such a way that we have only one variable involved. And let's look at this displacement ds in detail. So here we have the radius r, same as here. And if we have the magnitude of this displacement, if it's small, it's almost like a straight line. That's the approximation. So that's going to be the ds, and that corresponds to an angle d theta. So from this piece of geometry, we get that the length of ds is in fact the radius times the d theta, which is measured in radians. And substituting that here, and we have f times r d theta cosine theta. And we can take the constant terms out, so f is just the gravity, so that's going to be constant, and r is constant, so we have fr cosine theta d theta. And we integrate from the initial position where the theta is 0 to final position, let's just call it arbitrarily theta final for now. If we carry out this integration, we get from 0 to theta f of sine theta. And this is f times r times sine of theta final minus sine of 0, which is 0. So we get fr sine of theta f. And f is just mg times r times sine f. We want to find the work when the pendulum or swing has swung all the way down, in which case the theta f is 90 degrees. So let's do that. So in that case we get mg times r times sine of 90 degrees, and that is 1, so we get mgr. At the very bottom here, the r is just the initial height of the object. So this is the amount of potential energy that is being converted into kinetic energy. And it's gravity that does this job of converting energy from one form of another, in this case from potential energy into some kinetic energy at the bottom.